Hello, everyone. Today we're going to talk about short-term reliability. This is the second in a two-tutorial series on system stability. Sorry. Okay. We've got some acronyms and definitions here for your reading pleasure later. So first, let's talk about fault ride-through. And let's talk about the difference in fault ride-through between a synchronous generator and an inverter-based resource. So for a synchronous generator, they've got two operating modes, on and off. So everybody knew that. You'll see in the next slide why I mentioned this. We talked in the last tutorial about how the fault ride-through behavior of a synchronous generator is driven by the physics of the synchronous machine. And Nick explained how during the fault, the generator speeds up, and depending on how fast that fault can be cleared and how fast that generator can get back online, that generator may have sped up so much that it can't get back in sync with the grid, or it may be able to get back in sync with the grid. So this is the physics of synchronous machines. We also talked in the last tutorial about how synchronous generators are electromechanically coupled to the grid frequency. There's all this big rotating mass, and it's all spinning at 60 hertz. And synchronous generators have protective relays that protect them against equipment damage. You can imagine it could be really expensive if you damage that big, complicated rotating mass. Now, in order to deal with minor speed bumps on the system, NERC has set up a standard, NERC PRC 024-2. And this standard tells generators how NERC wants them to stay online during voltage and frequency speed bumps on the system. So you'll recall that we said in the last tutorial that the system's designed for redundancy. So if I lose a big generator, I lose a big transmission line, frequency may dip, voltage may dip. That's okay. The system is designed to work around that and to keep humming along without missing a beat. And this behavior is called ride-through. We want the generators to stay online during these speed bumps. And this graphic here is showing the voltage ride-through envelope for this NERC standard. And it's basically saying that within this pink no trip zone, you have to make sure that your settings on your protective relays are set so that you don't trip offline during this pink zone. And we've got voltage here on the y-axis and time out here on the x-axis. And there's a similar envelope of operation for frequency. And within a certain frequency excursion band, we don't want generators to trip offline. We want them to stay on, continue operating, continue supporting the grid. Okay, so inverter-based resources are different. Now, inverter-based resources, it turns out they've got three operating modes. There's on and there's off, but there's a third mode called momentary cessation. Momentary cessation is when an inverter senses that the voltage is abnormal, it's outside of normal operating ranges, and an inverter blocks the injection of current and the injection of power into the grid. So it momentarily stops injecting power into the system. And then it waits until voltages get back to the normal range, and then there's a lot of programmed behavior. It might have a delay, it might have a ramp rate back up to full output again. So a lot of this gets programmed in. The big difference between that and being tripped offline, so in the tripped offline, the off state of an inverter, they also are not injecting current or power into the system. The delay time before it returns to service when it's in the tripped mode is usually longer. So it's usually 5 minutes or something like that before it can go back into service if the grid conditions are okay. Again, this stuff is power electronics. So inverters are programmed. A lot of this behavior is just programmed behavior, and we can change those programs, as you'll see. It's important to note that we described this in the last tutorial. Inverters essentially measure the voltage and the frequency of the system, of the grid. But if they measure that too fast, they may measure a transient. And if they measure and respond too fast, they may be responding to something that's not real, and they may overreact. This graphic here on the right, this is a similar kind of graphic to the one that I showed on the last slide in pink. So that was from the NERC standard about how to set your protective relays and showing where NERC wants generators to ride through voltage blips. This is also a voltage ride through envelope. This is taken from the IEEE 1547 standard for distributed energy resources. This particular one is from a category of resources that was really designed around inverters in mind. And you can see this is a lot more complicated. The gray parts tell you where you should trip. The green of this, the continuous operation capability, shows you where voltages are normal and you should be injecting current and operating normally. This blue part shows you where voltages are abnormal, but you need to continue to inject current into the system despite the fact that voltages are abnormal. And then this orange part that says permissive and this blue part that says permissive, these are areas where an inverter, it can continue to inject current normally, or it can go into this momentary cessation mode that we described, where it blocks its own action of injecting current into the grid and waits until voltages get to a level where it can go back to injecting current into the system. So that's an example of some of the thinking that's going into how inverter-based resources behave during events. While we're on the subject of 1547, I want to make a pitch to you that the 1547 DER interconnection standard that we've been using for many years, you probably know this already, has been revised in 2018. And let me just give you a little bit of history. The old IEEE standard was designed 20 years ago, back when we didn't expect to have high penetrations of DERs, where safety was the biggest concern, and where we wanted DERs to trip offline if there were any speed bumps on the grid. So just trip offline, get off the grid, because we were afraid that it might accidentally energize a downed part of the distribution system. So this old standard, it wasn't designed for DERs to support the bulk power system. It wasn't designed for high penetrations of DERs. The new standard that just came out a couple of years ago supports high penetrations of DERs, and it requires DERs to support the bulk power system by riding through the voltage and frequency speed bumps on the grid. We suggest that, I don't know what your region in particular, what standard you are using, but we suggest that you move to this new standard because, one, it helps you accommodate more DER. You can actually put more DER in a feeder with the new standard. And two, it helps all of the Western interconnection maintain grid reliability during events. So it supports the bulk power system. Okay, I'm going to talk now about a couple events and some of the things that happened with inverters during these events. These were big learning experiences for the industry. So the first event is the Blue Cut Fire event from 2016, where 1,200 megawatts of PV came offline and did not ride through that event. So this was back in 2016. There were some fires in Southern California, and there were over a dozen transmission faults during that time. And there were a number of events where PV came offline. And there's been a number of events since. These events, these transmission fault events, were not unusual in any particular way. They cleared very quickly. These are the kinds of speed bumps that generators are designed to ride through and required to ride through. So what happened here? What went on? First of all, 700 megawatts of PV incorrectly measured frequency and tripped offline. I want to stop that. All right, reset. First event I want to talk about is the Blue Cut fire event from 2016. So there were some fires in Southern California, and on this particular day, there were over a dozen transmission faults. None of these were really unusual. They cleared very quickly, but 1,200 megawatts of PV did not ride through one of these events, shown here with the number 1. You can see the drop off of the 1,200 megawatts of PV right there. So what happened in this event? First of all, 700 megawatts of PV measured frequency and tripped offline in 10 milliseconds. So to give you an example of how fast 10 milliseconds is, if I look at one waveform, you know, the sine wave of 60 hertz, one waveform of that is 17 milliseconds. So this PV tripped offline before it could even read the whole waveform. So it incorrectly measured frequency, thought frequency was much lower than it was, and tripped offline. 450 megawatts of PV went into this momentary cessation mode, where it saw that voltages were depressed or low and blocked injection of current, and then it had some delay, and then it started to ramp output back up, and that took a while to go through all of that. So that was 450 megawatts PV. Then there was 100 megawatts of PV that was trying to go into the momentary cessation mode and tripped because of overcurrent protection. What you can see down here on the bottom right is that it took about 7 minutes for a lot of this PV to come back online. And some of the PV never got restored to service on this day because it ended up being curtailed by its operator. But you can see it took 7 minutes for this to come back. And as you'll recall from the last tutorial on frequency, we're trying to restore frequency. Minutes is a long time in the frequency world. And a frequency event did occur from this loss of PV. Luckily, there was enough frequency response in the system to manage that. But you'll recall that the frequency design basis in Western Interconnection is 2750 megawatts, right? Loss of 2 Palo Verde units. This is almost half of that. So this is a significant loss of generation. At the time, simulations were done to see how much PV could be at risk for other credible fault events. So some simulations were done looking throughout the Southern California region, putting faults in the 500 kV system in that region, and looking at how widespread depressed voltages would be in that region and how much PV that might cover. And calculations suggested that it was up to 7,000 megawatts of PV. So this was a really big deal. This could have potentially had worse consequences. It's important to note, so this is an inverter-based resource issue. As far as we know, distributed energy resources did not trip offline or momentarily cease due to this. Wind was not affected by this, but other IBRs, we do need to consider that and be careful about that. And batteries are another growing inverter-based resource that we need to consider here. As a result of this, NERC and IEEE are developing a new standard, 2800, and this new 2800 standard is addressing these kinds of issues for inverter-based resources on the bulk power system. The idea here is we need all generators to ride through speed bumps on the grid. The stuff I showed you in the last slides were for distributed energy resources. IEEE P2800 is going to address inverter-based resources on the bulk power system. And NERC has since come out and issued guidelines on trying to reduce this momentary cessation or eliminate it if that's at all possible. And since this event has happened, PV owners have gone back and OEMs have reprogrammed the inverters, and a lot of this has been managed and fixed. And that was shown through subsequent events that a lot of these particular issues were fixed. Okay, now let's talk about DERs. So in 2018, there were some Southern California events where distributed rooftop solar did not ride through. And these two events I'm showing here are the Angeles Forest and the Palmdale Roost faults. Again, transmission faults cleared in a couple, 2 or 3 cycles, not unusual, but rooftop PV in SoCal Edison's territory tripped or momentarily ceased output. They noted that PG&E was not affected by this. And the way, so you can't, we don't have monitoring of our rooftop solar. So we don't know the output of the rooftop solar. The way to get at the output is to look at the change in the load, change in the load that SoCal Edison sees or the Cal ISO sees. So unlike the previous event where we could just go back and look at the data from each utility scale PV plant, here you've got to try and tease out what's happening. So the Cal ISO net load change is sort of teased out here on the right. And SoCal Edison basically went into each of their substation bank SCADA points and pulled out the actual data and aggregated up the net load change and determined that there was about 130 megawatts of rooftop solar that came off for the Angeles event and 100 megawatts for the Palmdale event. And this picture is just some anecdotal evidence. Someone took a picture of their inverter readout that day, showing that for their inverter, it tripped offline at the time of the event and then came back on 5 minutes later. The net load increase lasted about 5 to 7 minutes, which correlates with the times in the IEEE 1547 standard. So the key points for fault ride through are that we want all generators, whether they are inverter-based, whether they are distributed, we want them to ride through minor voltage and frequency events and continue to support the grid. Also, inverter-based resources can be designed to provide better ride-through performance than synchronous generators. And that's really highlighted in the 1547, the new 1547 standard, where there's different categories, the most stringent of which synchronous generators would find a hard time trying to meet. We note that superior performance can be valuable. And then, as NERC points out in their guidelines, we should really eliminate the momentary cessation if possible. If you have IBRs that are going into momentary cessation mode, then you should try and minimize that impact as much as possible by getting them back into service and getting them back up to full output as soon as possible. Okay, now we're going to switch gears and talk about grid strength. So this is a graphic from Matt Richwine when he was at GE, looking at what is grid strength. So the analogy that we've got here is a trampoline. So a strong grid you could think of as a really good brand new trampoline, and the bed of that trampoline is the voltage. And a fault is a guy jumping on that trampoline. So when a transmission fault occurs, if you've got a strong grid, the voltage doesn't change much. Now let's take a look at the weak grid. The weak grid, half the springs are missing, a weak trampoline. And here, when a fault hits this weak grid, bus voltages change a lot. Now we're talking about voltage here. So you'll recall in the last lecture, voltage, unlike frequency, is all about location, 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 location. So this is all very location sensitive. All right, so grid strength is kind of like when we discussed in the last tutorial, there's an electromagnetic flux that synchronizes and locks together all the synchronous generators on the grid, right? It's one big machine. And it's that synchronizing torque that is grid strength. And in order to be in a place that has grid strength, you need to be electrically close to synchronous machines. So electrically close, what does that mean? So it's not the same as physical distance. Electrically close means big fat transmission line to a synchronous machine. If you had a long, stringy transmission line to a synchronous machine, that would not be electrically close, and that would put you likely in a weak grid position. Okay, so synchronous machines, synchronous generators, synchronous condensers, they all provide grid strength. Today's inverter-based resources, so today's PV, today's wind, today's batteries, do not provide grid strength. Now, there may be changes to that in the future with new technologies. We'll talk about that in a different tutorial. Okay, how do we know when we're at risk? So there's a bunch of metrics. They're all based around this idea of short circuit ratio. So you take the short circuit strength at a location, compare that to the megawatt rating of the generator that you want to put there, and that gives you your short circuit ratio. And depending on what that short circuit ratio is, that gives you a sense of whether you can operate there. So you'll recall, we said this in the last tutorial, that inverters, they basically read the voltage and frequency on the grid. They need a strong signal to be able to read, so they can lock into that with a phase locked loop, sync up to that, and then inject current that matches that. So basically when that signal gets too low, they can't lock into that stably. So they've got to have a strong enough grid to lock in and stably operate. And what this metric is showing here is for wind, when you're up around 7, 8 a few years ago, you could operate, but you got below that, things started to get hard. Today, this has gotten much better. Now we can operate at short circuit ratios of 3 and less. And the manufacturers of inverters are every year designing better and better controls and making their inverters able to work in weaker and weaker systems. So this is always improving. I should note that if you have a new wind plant with new controls and you put it into a weak area, you might be able to operate in that weak grid, but the other generators around you, who maybe they're 10 years older with controls that are 10 years older, and you're making the grid weaker by entering into that market, they may not be able to operate in that level short circuit ratio. So you have to also consider as a planner what all of the other plants are able to do. So grid strength, a lot of folks probably haven't even heard of this. It's not a market product, it's not an ancillary service. And yet there are systems around the world, ERCOT, South Australia, Ireland, that are having issues with this because they have high penetrations of inverter-based resources. So how are they managing? Some of the things they're doing things like running synchronous generators as reliability must run, dispatching them out of merit. That might increase wind and solar curtailment. That's got economic consequences. On a system level, you could build more transmission to alleviate weak grid issues. We can fine-tune the controls of the inverter-based resources. In some regions, they're installing synchronous condensers, and Nick is going to talk about that in a minute. And then there are new technologies that are potential solutions for the future. And with that, I'm going to turn it over to Nick to talk about small signal stability.